Sorry I could not be with you today. However, we are going to start Unit 2, which is chemical reactions. We'll start off talking about the law of conservation of mass and balancing. These are review topics, so these are things you have done in grade 10. I will go through the PowerPoint with you fairly quickly today, but you can always go back and read and listen to it again, and it will be posted on the class site. So here we go. We know that chemical reactions occur. We know they are interactions between chemicals. In any chemical reaction, you have a reactant and you have a product. Of course, the reactant is the substance that undergoes the chemical reaction. It is the ingredient. The product is the substance that is formed in a chemical reaction. So that is the end product, what gets made once the reaction occurs. So a chemical reaction, what it is, it's a process. And in that process, you get the creation of a new substance. And proof of that new substance is in the evidence. You will get gas given off. You may see a precipitate formed. You may get a color change. You may get heat or light absorbed. So these are pieces of evidence that show that the chemical reaction has taken place and a new substance has been formed. Now, we don't want to write down a lot of stuff, so we use a short notation form, and this is where we get the chemical equations to represent the components of the chemical reaction. So in this situation right here, we have methane, CH4, we have oxygen, and that produces carbon dioxide plus water. And it's a lot faster to write that in the chemical equation form than writing it out with words. The things that an equation will show, first of all, it will show the reactants. The reactants are going to be the ones on this side, and they are going to create the products. The products are the ones that are formed. The arrow in the middle is represents produces. So methane plus oxygen will produce carbon dioxide and water. Of course, we can still use word equations, and now that you're all pros with naming, you know that something like sodium and chlorine will give us sodium chloride. Now, the skeleton equations you learned last year in grade 10, skeleton equations, and basically what this is, these skeleton equations give us, it's like the ingredients in a recipe. So in order to make sodium chloride, you must need sodium and you must need chlorine. Just like in order to make pancakes, you must need flour, water, sugar, and butter. Now the problem, we don't know how much of each of these ingredients we need to get this in product. So these are our reactants, this will be our product. And that's what a skeleton equation is. It's just the bare basics. It tells us just what we would need in order to make something. It does not, however, tell us how much. We will get to that in a minute. Also in the skeleton equations, which is new, I'm not sure if you had to do it last year or not. I know I teach it to my grade 10s. We are going to incorporate the states of matter this year. So if we look at what we have here, a little s tells us if something is a solid. We have G for gas, L for liquid, and AQ for aqueous. Now remember what I said last time in the last unit. Acids, we will always see AQ near acids. Acids are aqueous, but not everything that's aqueous is an acid. So there are many other things that will have this aqueous symbol, and we will talk more about that a little bit later. But for now, if you look at sodium in the periodic table, it is a solid. If you look at chlorine in the periodic table, it is a gas. And we know salts that are formed from a metal and a non-metal will be a solid because we have that crystal structure. Law of conservation of mass. I know last year that you did a chemical reaction where you put a substance in a flask, you stoppered it, you threw in a solid, you threw in a liquid, you inverted this, made the reaction occur, and when you weighed it on the scale, the mass should have stayed the same. Okay, so the mass of the reactants equals the mass of the products. That is the law of conservation of mass. So that means now if we go back to our skeleton equation, let's just ignore this right here for a minute. Let's pretend that's not there. We know when we want to make sodium chloride, we must need sodium and we must need chloride. Don't forget, this is a diatomic molecule. This is the Hofbrinkel. Hydrogen, oxygen, fluorine, bromine, iodine, chlorine. Okay, so these are the Hofbrinkels. They are diatomic, which means when they're by themselves, they exist in pairs of two. So hydrogen will be H2, oxygen O2, chlorine, bromine, and so on. Now, this means if we have two chlorine atoms, let me just make some space here. That means we have a chlorine and a chlorine. And we know we have a sodium. Again, let's just get rid of this and this for now. When we have this present, we know we can make a sodium chloride that join together. So we get rid of this one, we get rid of this one. But we have a chlorine left over. That doesn't just float there and stay and do whatever. Instead, it will join with another sodium that's around, which means there must have been another sodium around to begin with. So in order to make sodium chloride, okay, because we have chlorine, we have two of them, that means we have the potential to make two sodium chloride molecules. And in order for that to happen, there must have been two sodium present as well. So we need two sodium, we have two chlorine, and that way we can get two sodium chloride molecules. The two in the front, this and this, these are your coefficients. So we have this coefficient, we have this coefficient. This two right here is a subscript. The only ones that we can change are the coefficients. We cannot change the subscript. So if we have, for example, MgO, we cannot say put a 2 here just because we want to. You cannot change the actual molecule. You can change how many of them you have, but that's it. Let's move on. So going back to the law of conservation of mass, atoms are not created or destroyed, they are rearranged. And that's it. So in order to have 1, 2, 3, 4, 5, 6, 7, 8 molecules of water, if that's what this is, you must start with 1, 2, 3, 4, 5, 6, 7, 8. And then you must have 16 of these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. It doesn't matter how big the bang is, the mass will not change. And even from the 1990s, it doesn't matter what happens, the mass does not change. Okay, let's go back to the symbols in chemical equations. I was saying earlier we do have gases, liquids, and solids, and of course the aqueous notation. So these are substances that are in solution with water. So if you add sodium and chlorine and you dissolve it in water, you now have aqueous sodium chloride. Here are some steps to balancing chemical equations. Basically, the biggest thing that I find, always leave oxygen to the end. That's probably the hardest one sometimes to balance, and we'll look at examples why. Things to remember, I've already brought these up. Hofbrinkel, okay. Diatomic elements when they stand alone. Make sure this symbol means yields or produces. A lot of times as well, we will add a delta sign above an arrow if heat has been added. So we may have reactions like CH4 plus O2 if heat is added to then create the products, whatever they are. Double arrows, this shows that the reaction is actually reversible and can go in both directions. So there will be some examples where we may say this goes like that, but it also can go in that direction. Probably the biggest mistake that students make is changing the formula. You cannot change the formula of a compound during the balancing. The only thing you can change is the coefficient in front. So let's look at this one. We have iron plus oxygen to produce iron oxide. Now I know that's not the proper name. We have 2 iron here. Okay, let's start this again. We have iron plus oxygen to give us iron oxide. We know that if we have Fe2O3, we know that oxygen has a 2 negative charge, and we obviously have 3 of them. We know iron, we have 2 of them, so this must be a positive 3. So this is actually iron 3 oxide. And we cannot change that. So the only thing we can change are the coefficients in the front. So if we have iron, oxygen to produce iron 3 oxide, we have to figure out how many of each we have. So we have 2 iron on this side, so we must need 2 on that side. We have 2 oxygen here, we have 3 here. The only way to change this is if we put a 3 here to make that 6, and a 2 there to make that 6. 3 times O2, remember O2 is that we have 2 oxygens joined together, and we have 3 of them. So that means we would have 6 O2s. Here we have 3 oxygens together, and we have 2 sets of those. So that's 6 oxygens. When we do that, We now have changed how many iron we have, and we have 2 F2s. So that means we have a total of 4, which means we have to now go back and erase this 2 to make that a 4. So our final equation is 4Fe, 3O2, and 2Fe2O3. And that's what we have here. Let's look at another example. We have CuNO3, 2 plus KOH, potassium hydroxide, and we have copper hydroxide plus potassium nitrate. So now we have to figure out how many of each we have. So let's start with the copper. We have 1 copper here, we have 1 copper here. We have 2 nitrogens, and we only have 1 on this side. So we're going to place a 2 in front of the KNO3. Once we place a 2 in front of the KNO3, we now have our 2 nitrogen, like we have our 2 nitrogen. That also, though, gives us 2 potassium. So that means we must have 2 potassium here. We have 2 hydroxide. We have 2 hydroxide. So we're fine. We also have 6 oxygen. We have 6 oxygen. So we have a balanced chemical equation. We have 1 copper, 2 nitrogen, 6 oxygen, 1 copper, 2 nitrogen, 6 oxygen, 2 potassium, and 2 hydroxides, 2 hydroxides. You can count the oxygens all together, it will still balance out, or sometimes you can just count the polyatomic ions and that works as well. So if we get rid of this, we can see CuNO3, 2, we have 2, 1, 2. The last example that we will look at very quickly, we have 2 carbon, so we must have 2 carbon over here. Okay, so if we look at this one, we have 2 carbon, we need 2 carbon. We have 6 hydrogen, we have 2 over here, so let's make that a 3 to make that 6. These are the hard ones because you have to leave the oxygen to last, and this is why. Right now we have 2 times 2, so we have 4 oxygen right here, and we have 3 right here. Now that gives us a total of 7 oxygen. On this side, the only place that we can modify the oxygen is right here, and no matter what number we use, we will get an even number. So here's the trick. We have 7 oxygen here. Let's make this 7 oxygen there. We have to multiply that by 2, so we actually have 14. If we multiply that by 2, we can multiply everything else by 2. So let's make 3 times 2 is 6. And 2 times 2 is 4. And now we have an equation that's balanced. So these are tricky. It takes some practice. We will talk about this again tomorrow when I return. And I do apologize for not being able to be here today. But what I want you to do now is try these for yourself on page 61 of your workbook. and do as many balancing as you can, and we'll take it up from there tomorrow. Have a great day.